everyone back to the Thursday edition of the workshop on learning in the presence of strategic agents. It's my pleasure. I'm Grant Chainabeck. It's my pleasure to introduce our first speaker, Annie Liang, who's an assistant professor in economics at Northwestern University, as well as the Carr family assistant professor in computer science. Annie's done really interesting and fascinating work on models and asking what makes a good model, and really digging down deep and providing interesting answers to these questions. And I hope she'll tell us more about that here now. So take it away, Annie.
Awesome. Thanks a lot, Grant. I apologize for not being there in person. I very much would have liked to be there, but undergraduate teaching started this week, so it just wasn't possible. But I'm delighted to be presenting this paper. This is joint work with Isaiah Andrews, who's an econometrician at Harvard, Drew Fudenberg, who presented earlier in this workshop, Chaofin Wu, who's a Northwestern computer science student. And the paper, so by the way, this is a new paper. It's our first time presenting this, so your feedback is going to be very welcome. So the paper is about the transfer performance of economic models. So what do I mean by that? Okay, well, suppose you train a model on data, okay? You might hope that the model that you get is going to be useful not only in the specific domain from which your data was drawn, but more broadly for predicting behaviors in other related domains as well. All right, so for a concrete example, suppose you have access to a data set consisting of evaluations of risky lotteries made by subjects in the United States. Let's call that our US data. You can use that to estimate a model of risk preferences. Okay, you might be interested in how risk averse these subjects are. Now, that model is certainly going to be useful for predicting future evaluations of risky lotteries, again, made by US subjects, but you might hope that the model is useful beyond that. So for example, if you were to predict evaluations made by German subjects, you might hope that this model would still be informative about that. Okay, maybe not quite as predictive as for US subjects, but still predictive. All right, now how well a model transfers is going to depend on whether the model has captured generalizable structure that holds across these different domains. And this property of whether a model is in fact transferable has become, I think, more interesting as of late, now that people are increasingly using black box algorithms in place of these economic models, right? So we can estimate an economic model of risk preferences, or we can train a black box. If you take that black box, you can use that equally to make predictions on the new data set. And it's always a little bit fuzzy, what we mean by black box versus economic model, but let me just highlight one key difference, which is whether the architecture is designed specifically for the setting you have in mind. Right, so this is a depiction of a random forest. We can use random forests to predict evaluations of risky lotteries. We can use essentially the same algorithm to classify whether an image has a cat in it. In contrast, economic models tend to be very tailored to the specific problem you're interested in. So this is a depiction of what's called a cumulative prospect theory. It's actually a model we'll talk a lot about today. And the idea here is that individuals have a value function over money, which treats gains and losses differently. Okay. Moreover, people misperceive probabilities, and there's a very specific parametric form for how these misperceptions are enacted. Okay, so this is a model that we can use to predict evaluations of risky lotteries. We probably can't use this to classify images. All right, so despite the increased popularity of black box algorithms, even for economic prediction problems, there's still quite a lot of reliance on these traditional economic models. And we think one of those reasons is because people have an intuition that economic models do a better job of capturing general structure than black boxes do. And thus, these economic models are going to transfer better across domains. Right? It's a very reasonable intuition. We don't know if that is in fact so. Right? So in this paper, what we do is the following. We first provide a framework for the transfer prediction problem. It's going to be a very straightforward extension of the usual statistical learning framework, where instead of out-of-sample testing, we're going to be looking at out-of-domain testing. Right, then within this framework, we're going to provide finite sample forecast intervals for the predictive performance of a model on unseen data from a new domain. Okay, so crucially, we're allowing for the distributions to differ across these different domains. And these intervals are going to be useful for evaluating economic models and black boxes alike. Right, then we're going to demonstrate the methodology by applying it to a specific setting, which is predictions of certainty equivalence for lotteries. And here what we find is that if we look at the classic out of sample test, right? So if we look at a within domain prediction problem where the training data and the test data are drawn from the same domain, then we find that the black boxes that we use outperform the economic model that we consider. Now, there's two possible reasons this is the case. So one possibility is that the black boxes are learning generalizable structure that the economic model misses, right? The economic model imposes certain structure. If there's structure that the model is missing, potentially the black boxes are learning something that's a general regularity across domains that we would like to know. Another possibility is that the black boxes are learning idiosyncratic details of the different domains, which do not in fact generalize across settings. Okay, so for example, 13 is an unlucky number in the United States. It could be that when that number appears in a lottery, subjects consider that lottery to be less valuable. If that same number is not unlucky in Germany, then it could be that the black box is potentially going to learn this idiosyncratic detail, which will in fact result in better predictions for the US population. But this detail may not be one that in fact allows the black box to predict well in the German data. Okay, so we can separate these explanations by looking at the transfer performance of these models, which is what we do. And we find that in fact, although the economic models have worse performance out of sample within domain, they do in fact transfer more reliably across domains. Okay. This suggests then that the representation that the economic model is learning is indeed more general. All right, so a couple of comments on the relationship to the literature. So there is a literature called Domain Generalization within computer science. So in a sense, we're contributing to this. There's a difference in focus where this literature is more interested in developing new algorithms with good out-of-domain generalization. We're going to ask instead, if you fix a given model or procedure, can we provide a confidence interval for the out-of-domain generalization error of that model and procedure? Okay, within economics, there's a literature on meta-analyses. So these papers typically focus on how much an estimated parameter varies across settings. So you might look at, say, this risk aversion parameter. We're going to focus instead on the accuracy of the model's predictions. So these are related, but different. So for example, you could have very stable parameters across settings, but still the model's transfer performance could be very poor. Okay, finally, there's been a recent literature looking at how black box methods and economic models differ from one another. For example, there's been recent papers that demonstrate that black box methods actually outperform economic models in out-of-sample tests across various problems. So our results complement this by suggesting that these black box methods may nevertheless be worse at transfer prediction. So these are both important angles on this comparison, and this is just another comment on it. Okay, so are there any questions about the goals of what we're doing? Okay, so if not, let's go into the framework. Okay, so as usual, there's going to be a feature space X and an outcome space Y. Okay, as usual, a sample is going to mean a set of observations, XY, drawn from some distribution on this space. Okay. Now, departing from the usual statistical learning framework, we're going to suppose that the analyst has access to metadata consisting of n samples. Okay, so for example, these might be an American data set, a Bulgarian data set, New Zealand data set. Okay, each sample, again, consists of these observations. And we're going to suppose that the metadata is generated in the following way. Okay, so we're going to assume existence of a distribution mu, okay, in the following space, where this first part is the set of distributions on this Cartesian product. Okay, so the set of possible joint distributions for x, y. The second part is the possible sample sizes. And what we're going to suppose is that each sample, Si, is generated by first drawing a pair, Pm, from this distribution mu. All right, then, once we've drawn this Pm, we're going to independently draw M observations XY from this joint distribution P. All right, we're going to abuse notation by writing this more simply as SI being drawn according to mu, understanding that that means really this procedure here. So then going back to our example, right, to generate this metadata, for each of these domains, what we do or how we model or understand this the situation is we're assuming that there is a pair PM drawn for each of these domains. Right, so again, remember this first one is this distribution on X times Y. The second is a sample size. Okay, we're drawing this importantly independently across each of these domains. Then we're drawing that number of observations from that joint distribution, collecting those observations that gives us our sample for each of these domains. All right, now this assumption that distributions are IID across the different samples is certainly restrictive, but it's going to be important for making progress on this problem, so we see it as a useful first step. All right, now the transfer prediction problem is as follows. So we have our initial metadata, so all of this is observed, and we're going to suppose that there's a new sample Sn+1, which is again independently drawn from the same distribution mu. Okay, this we don't get to observe. All right, then taking the usual decision problem, what we suppose is that the analyst is going to choose a strategy to use in this new target domain. So a strategy is a mapping from the set of observed features into actions. Okay. For example, the action might be a prediction of the outcome Y, right? So you get to see X, you're going to use that to predict Y. Okay. Then the accuracy of that prediction is measured using a loss function, which takes as input the action and the true outcome, outputs a number. Okay, so I'm saying prediction, it doesn't have to be a prediction, right? What's important is just that the payoff consequences of the action that you take depends on the realization of Y. Okay, and then as usual, we're going to say that the error of the strategy sigma on a given sample S, okay, which we're writing as E of sigma S, that's going to be the average loss of the strategy on observations from the sample S. Right, so for each X, Y in the sample, we're using sigma to decide what action to take. Then we're using the loss function to decide to evaluate the sort of the error or the consequences of taking that action when the true outcome is Y. All right, so eventually we're going to be interested in evaluating the error of a strategy that we pick on this unseen target sample. So then the crucial question is how we choose this strategy. And there's really two choices here. So the first choice is what part of the metadata to use for training. Okay. Now you might think that we just want to use all of the metadata. As we'll see, if we're interested in bounding your error on the target sample, sometimes it's going to make sense not to use all of the metadata, but instead to use some part of it for training. Okay. And second, and this is really the main content, you need to choose how to map the training data into a strategy for use on this target sample. And there's many different things you could do, right? You could train a black box, you can estimate an economic model. All right, so now in more detail, so the first part is choosing what part of the metadata to use. So we're going to let T here be a subset of the of 1 through N. And this T is going to index the samples that we're going to use for training. So MT here is going to be our training data, and that's defined as the union of all samples indexed by one of these training domains. So for example, we might say, okay, let's use the American data and the Bulgarian data for training. In this case, T would be the set 1, 2, and our training data would be the union of all observations in S1 and S2. All right, then we're going to choose a decision rule, rho, which is any mapping from samples, S, into a potentially randomized strategy, sigma. All right, so given this training data, what is the strategy that you want to learn? Okay, for example, you might use that training data to estimate the free parameters of an economic model, okay? Or you might use that training data to train a black box algorithm. What you get is going to be a strategy that you can then ultimately use for making decisions on this target sample. All right, and then this slide gives the crucial definition of transfer error, which we're going to be interested in bounding. So fixing a sample D, we're going to use this simpler notation E subscript TD to mean the transfer error when we use the strategy rho of MT. So this is applying the decision rule rho to the training data MT. Okay, so again, remember that's the strategy. So we use that strategy on the sample SD. Okay, and then we evaluate the average loss on that sample. Okay, that's going to be our transfer error. Okay, so any questions about the model or our definitions?
Yes, one question over here.
The transfer error comes from just using the data you have trained on independent from the transfer set, and just found the error on the transfer set. Does it mean you don't really consider things like potentially, depending on the data generating process, several data sets may have kind of neutralized some useful effect. So that's one. And the other, so learning a mixed strategy, like mixed data set, might not be the best model. And the second thing is that, so in domain generalization or machine learning in general, there's a notion of domain adaptation, where you somehow receive a few samples from the target, and then you kind of adapt your model and fine tune it for that domain. Does this setup kind of exclude that? Yeah.
Great. Let me start from the second question. So in this talk, I'm going to focus on just transfer error. But in the paper, we actually define another measure called transfer deterioration, where the question that we ask is, what is the value of obtaining new data from the target domain? So that's very similar to what you were mentioning, right? So here, I think you were suggesting using a little bit of data from the target domain. We go all the way and we ask, what's the ratio of your error if you were to use the metadata from other domains compared to if you were to have access to the target sample? But that's spiritually very related. The first part of the question, I'm not sure I completely understood. I think you were pointing out that the rules that we use are directly applied to the training data, not necessarily taking into account the data generating process. So if that's what you were saying, then I agree that that is correct. So just like when you train a black box algorithm, you're not adapting that algorithm necessarily to an underlying structural model of how the data was generated. But if I misunderstood the question, please let me know.
Yeah, thanks for the answers. Yeah, I think that makes sense to me. I guess the other worry was that there potentially could be a better model that's not kind of discoverable or does not score well under this measure, if that makes sense. Oh,
well, that's interesting. Okay, so that's certainly possible, but then we have to decide what we mean by better, right? Yeah. But yeah, let me just also say again that in contrast with the domain generalization literature, here we're not going to be so focused on finding the best approach for out-of-domain prediction. We're going to be interested instead of this question of, given a specific approach, how can we evaluate it? Was there another question in the back? I can't quite.
A couple more.
Yeah. Okay.
Hi. Let's see how to ask my question. I mean, there's a sense to me in which this looks kind of like a standard statistical learning problem, but somehow you've I don't know, embedded this kind of hierarchical structure or something in. But just looking at the slide we're looking at right now, we have all of our samples from, S1 to Sn drawn from a distribution. And I think you said Sn plus 1 is drawn from the same target distribution, I think. So I don't know. So I'm just a little confused. It seems to me like you could, maybe the right idiosyncratic black box model that's sort of designed for this setup, which maybe we haven't designed yet because we haven't worked hard on this particular setup, would possibly do just as well. And then I don't know, then we have to lift to the next hierarchy or something. I don't know. Do you see what I mean? It just—
Yeah, absolutely. No, so that's a great point. So the setting is in a sense isomorphic to the usual statistical learning framework. So certainly it's easy to see that this nests the usual out of sample test. If you fix the probability distributions to be the same across all the samples and take the sample size to be 1. You can actually also show that under the appropriate redefinition. So essentially thinking about the samples as observations, you can also nest this in the other direction. So, that's why I think of this as really a very straightforward generalization of the usual framework, but these new definitions are going to allow us to speak more clearly about the transfer prediction problem, okay, which is going to be especially useful once we go to the application.
Yeah, my question is I think fairly basic, and so apologies about that. I just want to understand, does this, I believe my understanding is that the relationship between X and Y can change between like your different samples. Right?
Exactly, yeah. Mhm.
And so if it can change in an unbounded way, like, right, like if my sample Sn plus 1 can be like completely arbitrarily, like the relationship between X and Y can be completely arbitrarily different, then you can say nothing, right? And so what you're doing is you're using the fact that these are all from some distribution. So you have kind of a distribution. Okay, is that
Okay,
basically
that's
right?
not basic at all. That's a fantastic summary
Okay.
of what's going on. Right, so the first important point is the sense in which this is at least superficially different from the usual out of sample test, is that the samples are drawn from different distributions, right? And they could be very different distributions, right? As you're pointing out, the assumption that we're making, and which is we're going to leverage substantially, is that these distributions are themselves IID from another distribution. Okay, and that's going to allow us to say some things. Okay, so that's a perfect segue then into our results. Okay, so let me tell you what we can say. Okay, so let me first give you a simpler version of our results, which is going to illustrate some of the underlying intuition. So let's start by fixing some subset T of observed samples to use for training. I think Drew has his hand raised.
Thanks. I just that the last question sort of echoed something from the previous question. So I just wanted to encourage you to slow down 30 seconds and make sure people track this. It's super important that it's not the same distribution each sample. Rather, the samples are exchangeable. And as Annie said, this is a higher level distribution, picking distributions. But maybe you should put that slide back up and talk a little slower and go over it once more, because it's absolutely key.
Sure, I think we can use this slide, right? So I think, okay, but hopefully people did understand. So let me just merge the two last questions then, maybe that'll be useful. So the sense in which this is different from the usual out of sample test is that we have samples drawn from different distributions. The question before that I understood as pointing out that since we've made this assumption that the distributions are themselves independently drawn from yet another distribution, there's a sense in which our setting can be seen as very analogous to the usual out of sample test if you think about these individual samples as themselves observations. Right? We're just imposing the independence at a higher level. Okay, great. So suppose we fixed some subset of samples that we're using for training. Okay, for example, S1 and S2. That's our training data. Now, here we're going to start seeing the value of using just some subset of the metadata as opposed to all of the metadata for training, which is that we now have a bunch of observed samples, which we can take as test domains. All right. So then for each of the test domains, which are in fact observed samples in our metadata, as well as for the new target sample, which we don't get to see, we're going to have a transfer error, which is the transfer error you get when you train on the initial chosen set of training domains, but then test for the subsequent. So here, for example, this ET of 3 is a transfer error from S1 and S2 to S3. Right, so on to ETN, and then finally we have the transfer error from the training samples to the target sample. So this gives us n+1 minus the cardinality of T transfer errors in total. And then here, this independence assumption, this ID assumption comes in crucially, right? So although the distributions governing these samples can be very different, because the samples are IID, we know that the ranks of these transfer errors must be uniformly distributed up to ties. So what I can do is I can order the ranks of the observed transfer errors. So this is the smallest to the biggest. And then the rank of the transfer error on the target sample, which remember is what we're interested in and don't know. that rank is equally likely to be at any of these positions indicated by the arrows. So therefore, we can bound the probability that the transfer error on the target sample is of rank greater than any R to be the following. Is that a hand in the back?
Yeah, sorry.
Yeah, go for it.
Is this seems very related to conformal inference to me.
Absolutely, it's exactly, yeah. This is those are the techniques we're using here.
Yeah, okay, cool. Thank you.
Right. Okay, fantastic. So we can use that to provide a one-sided bound, and we can use essentially the same argument for a two-sided bound, right? So fixing any RL and RH, the probability that the transfer error on the target sample is of rank strictly smaller than RL or strictly larger than RH can likewise be bounded. Right. So this is essentially a warm-up for our main result. We can use this argument to show that that we can produce a confidence interval for the target, the transfer error in the target sample, by looking at the RLth largest and RUth largest. So this is for R lower or upper observed transfer errors in our metadata. Okay, let me do that a bit more slowly. So for any R, let's define this to be the rth largest observed transfer error when transferring to test domains in our metadata. Right. Then the probability that the transfer error onto the target sample falls outside of this interval here, okay, is no more than this right-hand side. Therefore, we can take this interval as a two-sided confidence interval for this transfer error on the target sample, which we don't know, with the following confidence guarantee. Okay, great. So hopefully that gives some underlying intuition for how this IID assumption is going to be very useful. However, this previous approach makes a sort of weird choice, which is that we single out a set of training domains T to use for training a priori. Right. For example, I chose American Bulgaria in the example that we were looking at. But ex ante, all of these samples in the metadata are symmetric. So there's really no reason to use the American and Bulgarian data for training compared to, say, the American and Chinese data sets. So a very natural approach then is to randomize the choice of samples that we use for training. Okay, that's exactly what we're going to do. We're going to pick a fixed size. And we're going to randomize over all possible sets of training domains of that fixed size. Right. And our main results provides confidence intervals for the training error on the target sample when the set of training domains is itself random. And the approach is going to be as follows. What we're going to do is we're going to pool together all the transfer errors when we vary both the set of training domains as well as the test domain. And we're going to show that we can use quantiles of that pooled sample as the lower and upper bound for this confidence interval. All right, so let me do that in more detail now. So previously, we talked through how to provide a confidence interval when we fixed the set of training domains to be, for example, S1 and S2. Okay, as I was pointing out, there's no reason to pick 1, 2. We could pick 2, 3. So now what we're going to do is we're going to pool together all transfer errors from a set of training domains T to a new test set, which is outside of that training set. But we're going to do this for all subsets T of some fixed size N of T. Okay, so for example, if we were to fix T to be 1, 2, then the transfer errors in that case, and here we're only going to collect the observed transfer errors. So we're looking at the transfer error to sample 3 all the way to the transfer error up to sample N. Okay, we're not including the target domain. Now, if I change the set of training domains to be 2 and 3, now we have the transfer error to sample S1, okay, so on and so forth to sample Sn. We're going to do this for all subsets of size NT. That's going to give us a pooled sample of transfer errors. And then for any tau, for any quantile tau, we're going to define E of tau to be the tauth quantile of that pooled sample. Right. And our main result says that we can use that to provide, to construct confidence intervals for this quantity here. Okay, so what is this? This is the transfer error onto the target sample when the set of training domains is not fixed, but is instead a random variable whose distribution is uniform over all subsets of 1 through n of some fixed size n of t. And the main result says that if we pick any quantile tau, if we construct the confidence interval where the lower bound is the 1 minus tauth quantile of the pooled sample of transfer errors that we just constructed on the last slide, the upper bound is the tauth quantile, okay, then the probability that this transfer error onto the target sample is outside of this interval can be bounded as follows. Therefore, this interval can be used to provide is a two-sided confidence interval for the transfer error on the target sample with this guarantee. Okay. The main technical challenge here is that although we can use the previous argument to construct a confidence interval for each draw of t, these intervals are going to be statistically dependent across these different draws, and that dependence is something that we have to account for in constructing these confidence intervals. So just one more comment on this. So note that these confidence intervals that we're creating describe variation in the transfer error due to two sources. So first, there's the usual source, which is uncertainty because your data set is finite. There's a second source, which is variation in the transfer error due to the random selection of the training and test domains. Because of that second source of variation, we actually don't expect the length of these intervals to shrink to 0 as we acquire more domains. Okay, that might seem a little bit funny, especially if we're talking about confidence intervals. So therefore, actually, for the rest of the talk, I'm not going to call these confidence intervals anymore. I'm going to call them forecast intervals to make that distinction clear. All right, so any questions about these results? Otherwise, I'll subsequently go into the application.
Yes, we have a question.
Mm-hmm.
Sorry, there's something I really don't understand. When it's a forecast interval, in a way, when we apply this target interval, it does tend to be something that happens in the future, whereas the other domains we collected that we are able to train on came from, at least timestamp in the past. In that way, how would you justify the IID domain
Fantastic.
selection?
That's actually an example that we give for in the paper for why the IID assumption is restrictive, right? So if you have in mind a time series, then you very well may expect a correlation across these across these different periods, in which cases IID assumption doesn't quite make sense. I do want to say that I didn't mean to imply, so I might have used the word future in the talk, but there's no sense in which this target sample has to be acquired at a later point in time. What's crucial is just that it's unseen. All right, and so there's many different ways in which we might think of the domain. So different time steps is certainly one kind of domain variation, but as I'm showing in this example, another potential domain variation is just subject pools, right? So how American subjects think about choices between risky lotteries versus Bulgarian subjects. Great. Any other questions? Was that a no? I couldn't quite hear that.
It's a no. There was a
Okay.
person walking by outside on their cell phone.
Got it. Okay. All right, great. So then let's spend the rest of the time on the application. All right, so we look at a classic problem from economics, which is prediction of certainty equivalence. Okay, so the setup is as follows. A subject is going to be offered a risky lottery. So there's two possible prizes with corresponding probabilities. And we're going to ask, what is the dollar amount X such that the subject is indifferent between receiving the outcome, the random outcome of the lottery, versus receiving X dollars for sure. That dollar amount X, we call the subject's certainty equivalent for the lottery. Okay? But this is a prediction problem. I can ask you, if I just give you the lottery, can you predict the subject's certainty equivalent? So what we've done is we've constructed a metadata set consisting of samples of reported certainty equivalents from 44 subject pools. So here we're going to be interpreting domains as subject pools. I want to put a star on that. That's something we're going to come back to later. Okay, these samples come from 14 papers from experimental economics. So actually the samples, the the different domains that we're going to use, they differ actually not just in the subject pools, but also in other things like the framing of the lotteries. So we're going to expect that models of risk preferences that are trained on some of these samples will still be predictive of data in the other samples, but it's going to be imperfectly predictive, and we want to quantify how good that prediction is. So we're going to consider decision rules based on an economic model as well as two black boxes. Okay, the economic model is something called cumulative prospect theory. The two black boxes that we consider are the random forest and a two-layer neural net. So this part is probably more familiar for the audience, so let me just go through this in more detail. So cumulative prospect theory is a well-known model in economics for risk preferences. And the idea is as follows. So essentially, it's an embellished expected value, okay? But we're going to change two things. So first, we're not necessarily going to suppose that your valuation of money is linear. Okay, we're going to allow for curvature, and we're going to also suppose that you treat gains, or you interpret gains, differently from how you interpret losses. Okay, so this function here is the value function over money. It's described by this parametric form. There's two free parameters, alpha and beta. Okay, so whatever it is, so Z here is a dollar amount, V of Z is your valuation of that dollar amount. Okay, additionally, we're going to suppose that subjects don't in fact correctly perceive probabilities. So this part is really, both parts are inspired by large quantities of experimental evidence. So the idea here is whatever the probability is, there's actually some distortion going on in the subject's mind where you actually overweight small probabilities and you underweight large probabilities. So here, this W of P is the probability weighting function. So given true probability P, you perceive it as W of P, and that takes a very specific parametric form. Given here, again, that has two free parameters, delta and gamma. So then given a specific lottery, right, where these are the two prize amounts, P is the probability of the larger amount. This here, this is what I call the embellished expected value. That's going to be the utility of the lottery. And then this here is going to be the dollar amount that you consider equivalent in terms of utility to the lottery itself. So fixing any values for these four parameters, we're going to get a strategy. And this model we're going to identify with a set of strategies where we vary the values of the parameter. And here we're using range restrictions for the parameters that come from the literature. So the decision rule corresponding to this model is going to say, you give me the training data, I'm going to find the strategy in this set sigma star that best fits the training data, so minimizes error on the training data. That's going to be a strategy. We can use that strategy for prediction on the new target sample. Right, so that's our economic model. And then in addition, we have the two black boxes. So I'm sure this audience is very familiar, so let me not spend too much detail on it, but we train a random forest, which is an ensemble of decision trees, and we train a neural net, which implies these nonlinear transformations to the input features. So for us, the input features are simply the description of the lottery itself, so the two prizes as well as the probabilities. All right, so as a warm-up, before we get to the transfer exercise, let's first just consider the usual out-of-sample prediction problem. So what we're going to do is domain by domain, we're going to take the sample in that domain, okay, and we're going to split it into training and test parts. Okay, so in fact, we use the usual tenfold cross-validation. So we're splitting into 10 subsets using 9 for training, testing on the final choice. Okay, then averaging over the errors over the 10 possible choices of test set. And here, so the crucial contrast, right, between this and the transfer prediction problem, that's really our focus, is that here the training data and the test data are drawn from the same distribution. What that means is that given enough data, we're going to expect that the black boxes can actually learn detailed structure in that domain and outperform the economic model. Right, that is essentially what we find. So in 39 of the 44 domains, we find that the random forest error, out of sample error, is smaller than the out of sample error of the economic model. Okay, the improvement doesn't turn out to be large. So here, this is the CDF of out of sample errors for the random forest algorithm, that's the orange, as well as for the CPT model, that's the blue. Okay, and here we have a distribution because we have 44 domains. So we're looking at the errors across those different domains. Okay, you can see the curves are pretty similar. The orange curve is slightly better. We also actually looked at the in-sample errors. So that's going to further advantage the black box because we're not even testing out of sample. So the more flexible approach is simply going to be better. Actually, the CDF comparison, again, looks pretty similar. So the black box continues to be better naturally. And actually the difference, the more surprising thing is that the difference is not actually that large. Okay, so from these results alone, we can't distinguish whether CPT and the random forest are achieving similar out-of-sample errors by learning effectively the same representation, given the training data, or by learning different representations that just turn out to have similar errors. Right, so that's a puzzle. And then if the answer is the second, right, if they actually are learning different representations, is it the case that the random forest is achieving better out-of-sample errors by learning generalizable structure that the economic model is missing, or by learning idiosyncratic details of behavior in each domain, which in fact are not going to transfer across the domains? So we can tease apart these two explanations by evaluating the transfer performance now of these models using our main results. All right, so just to remind you, this was our main result. We said that if we looked at the 1 minus tauth and tauth quantile of transfer errors, of observed transfer errors, that would give us a confidence interval. Here, n, recall, is just the total number of samples in the metadata. That's just fixed, right? For us, that's 44. The other two parameters are going to be choices that we make. So n of tau is the number of samples in our metadata that we're using for training. And then tau is the percentile of the pooled transfer errors that we're going to be using to construct these intervals. In principle, we can choose any choice of tau. That's just going to give us confidence intervals of different levels, of different widths. Okay, the wider confidence intervals are going to correspond to lower confidence, higher confidence guarantees. And here we're going to set n of t to be equal to 1, and we're going to set tau to be 0.95. Right, so we're looking at the 5th percentile and the 95th percentile. And that's going to allow us to answer the following question. So if I draw one domain from my metadata at random, I use that one domain for training, I apply my decision rule, get a strategy, use that strategy to predict in a new domain. What is the 71 percentile, 71% forecast interval for how well I'm going to do on this new domain? And 71 here is applying our result here to figure out what the confidence guarantee is. All right, and here's what we find. So these are the 3 forecast intervals. Okay, the main takeaway is that the upper bounds for the 2 black box methods are substantially larger than the upper bound for the economic model. So the random forest upper bound is about twice as large. The neural net upper bound is even larger. And note that this is despite the fact that we saw that within domain, the out-of-sample errors were actually quite similar, right? So that's intriguing because it's telling us that although these representations that the economic model and the black box algorithms were learning had similar errors out of sample within domain, the representation that CPT is learning does indeed have different implications in these transfer prediction tasks compared to the representations that were learned by the random forest and the neural net. And moreover, the representation learned by CPT seems to be generalizing substantially better, right? So for this new domain, we can be pretty certain that the transfer error is going to be in this range. For the black boxes, there's a possibility it's much larger. Right. You might also notice that here the forecast intervals are overlapping. That's actually less informative than it seems initially. So the reason is this observation that we made previously, right? So these intervals are reflecting in part variation in error due to the random selection of training and target domains. So we're going to expect an overlap in these forecast intervals, whenever the CPT error on the upper tail training and target domains, or in a sense, the worst case choice of training and target domains, exceeds the black box errors on the lower tail or best case choices of training and test domains. Okay. So whenever this is the case, which is kind of a weak property, then we would expect the distributions of training errors to be overlapping, and then correspondingly, it's not surprising for these forecast intervals to also be overlapping. All right, so there, remember, we chose a very specific choice of tau to use to construct the confidence interval. We could have chosen different choices. So I think this figure is actually quite useful. So what we're showing you here is the x-axis is the percentile. It's essentially tau, but percentiles instead of quantiles. The y-axis is the transfer error. So what this tells us is fix any of the given methods, fix your favorite percentile. What is that percentile of transfer error in the pooled sample of transfer errors? And essentially, we used this figure to produce the original confidence intervals. Okay, also, if it helps, this is an inverse CDF. So previously what we did is we picked arbitrarily tau to be equal to 0.95. So then 1 minus tau and tau, right, we looked at what that percentile of transfer error was. Okay, for example, let's take the neural net. Right, so what is the 5th and 95th percentile of transfer errors using the neural net? Those two numbers gave us the two bounds for our confidence interval. So this is just showing you for the forecast interval. So this is just showing you the forecast interval vertically, but that's exactly what I showed you here a moment ago. And then of course, we don't have to choose 5 and 95. You know, if you want, you can choose tau to be equal to 0.75. So then we've got 25 and 75 as the two percentiles. Again, we have the corresponding numbers. Again, we can produce a corresponding forecast interval. It's just the confidence guarantee here is going to be lower, corresponding to the more narrow forecast interval. But you can see that whatever tau you choose, right, because the two curves for the black box algorithms are everywhere above the curve for CPT, it doesn't really matter what tau you choose. We're always going to get these forecast intervals for the black box algorithms that qualitatively have the same comparison with the economic model. So we're going to get wider confidence intervals with much larger upper bounds when we consider the black box methods compared to the economic model. Right, and also from this figure, what you can see is that although these curves are everywhere above for the black box algorithms compared to the economic model, in this region, actually, they look very similar. Right, so up to about the 55th percentile of the transfer errors, the methods actually aren't really that distinguished from one another. So what it tells us is it's not that the economic model sometimes does much better at transfer prediction than the black box methods ever do. Right, the best case transfer errors are actually pretty similar. The distinction is really that the black boxes sometimes do much worse, right? They sometimes achieve transfer errors that you're just never going to get if you use the economic model for transfer prediction. All right, so that concludes the main part of the results, but I want to talk about this choice now of how we define the domains. So how the forecast intervals should be interpreted very much depends on how the domains are defined. Right, so for the main analysis so far, we've defined it as subject pools. So are we looking at American subjects or Bulgarian subjects? Now, we don't view it as possible or even desirable to provide a measure of transferability that's not going to be sensitive to that definition. And in fact, we can apply results to different definitions of domains to understand across what dimensions a model is going to transfer better or worse. And we can, in fact, look at that within our specific application. So what we do next is we redefine domains. Instead of subject pools, we're going to define domains as papers, right? The papers from which we got the data sets. In this case, our metadata is now going to consist of 14 samples instead of the original 44, where each sample comes from one of the 14 papers that we used. And we can conduct exactly the same analysis. All right, and this is what we find. So this on the left-hand side is the figure we were looking at a moment ago. On the right-hand side is the same figure that we get if we now have the domains defined as papers instead of subject pools. And the main difference you can see here is that this region that we were discussing a moment ago, where the three methods look very similar, okay, now we actually do get separation, right? So from the very beginning, it's clear that the black box transfer errors at every percentile are clearly higher than the corresponding percentiles for the econ model's transfer errors. Right. So it seems like CPT's generalization ability is actually becoming more pronounced when we're transferring across papers rather than transferring across subject pools. All right, so that's a puzzle. Why is that the case? And so to the best of our understanding, this is what's going on. So one of the 14 papers that we're using is actually a meta-study. That paper itself consists of 30 samples of certainty equivalents from 30 different countries. Now, in the first analysis, we treated those 30 samples as distinct samples. So that means that we considered transfer prediction tasks, training on one of those 30 samples and predicting another. Right. Now, transfer errors between samples of this paper constituted 870 of the total 1,892 transfer errors that we've looked at. So that's actually a sizable component. In the second analysis, when we've defined domains as papers, we've merged these 30 samples now as a single sample. So we're no longer considering transfer prediction between those or across those samples from this paper. All right, so now we can ask, what's going on? What's special about the transfer prediction tasks between samples in this paper? And we can understand that by, again, repeating our main analysis, now limiting to these 30 samples as, again, a new definition of domains. All right, and here's what we find. So now these three curves for CPT, the economic model, and the two black boxes are virtually indistinguishable from one another. So this is telling us that CPT's transfer performance across samples in this specific paper doesn't actually seem to be better than the black box's ability to generalize. All right, so what's going on? Why is that the case? It turns out that the 30 samples in this paper involve certainty equivalents that are reported for the same lotteries. So what the authors did is they went to different countries, right? 30 different countries. They were asking different people, but they were asking different people the same questions, which is, what are your reported certainty equivalents for this list of lotteries? Okay. That list didn't vary across samples in this paper. It did vary across different papers. Now, it turns out that the variation in the average certainty equivalent across different countries for each of these lotteries is not large. I can actually, let's see how we're doing on time. I can actually show you. So the x-axis is the different lotteries, and the different dots for each of these lotteries are different average certainty equivalents for the 30 countries in this paper. And what you can see is, of course, there is some variation, but that variation actually doesn't turn out to be that large. So what the black box algorithm can do is essentially learn a table lookup procedure where you just memorize for each of these lotteries what the average certainty equivalent is for those lotteries. Now, it's not going to be a perfect prediction, right? So if you start with the Vietnam data, you learn the average certainty equivalent for these, say, like 28 lotteries using the Vietnam data set. That's not going to be a perfect prediction for the US data set. But because this variation is not large, it's not really a bad algorithm for prediction. All right. Note that the black box can therefore achieve reasonably low transfer errors across these different sample sets without actually learning how to extrapolate to new lotteries. Right? You can extrapolate to prediction of other countries' answers for the same lotteries. We're not testing you on how you're going to do is asked to predict certainty equivalents for new lotteries outside of this data set. So this provides a reasonable, interesting conjecture. Let me quickly take a look at the chat. Okay, 5 more minutes. Okay, so we might conjecture then that black box methods are going to perform worse when the domains are different in terms of the underlying problem instances that we're looking at, and when the domains require, when this transfer prediction problem requires farther extrapolation, that's exactly when the black box methods are going to do worse relative to the economic models. So this is a conjecture we've posed. It's not something that we've pursued in great detail. It's also an interesting question of just even how you would define farther extrapolation. Okay, I want to leave a bit of time for questions. Okay, I guess we've got 3 minutes. So let me just quickly tell you these other 2 things that are in the paper that I skipped in the talk. So first, so what I've shown you is confidence intervals for the random transfer error. In the paper, we also provide finite sample confidence intervals for quantiles of the transfer error. So for example, you might be interested in providing an interval for the median transfer error. So we have that, the results are qualitatively similar to what we looked at in the talk. And we also provide finite sample confidence intervals for the expected value of the transfer errors. Right, so just to be clear, we've got the random transfer error, the quantile, and now the expectation. And here our confidence intervals use bounds on what we call transfer Rademacher complexity. So essentially leveraging this analogy between the usual statistical learning framework and our transfer learning framework, we can adapt existing results for our setting. So here we provide an analogous definition of Rademacher complexity for this transfer prediction problem. Using that, we can develop these bounds. It turns out that the bounds that we get aren't very informative in our application. They're just huge. Actually, so for this audience, if you know about empirical applications of Rademacher complexity in computer science, where those bounds have been useful, I'd be very curious to hear, because our understanding so far is that they're useful for classification problems, but not necessarily useful for other loss functions. Was that a comment? Okay. So anyway, so we do provide these bounds in the paper for use in other applications, but this is the reason we don't emphasize it in our paper. Okay, so just to conclude, our results quantify how well a model's performance on one domain is going to extrapolate to other domains. In an application, we've shown that the predictions of CPT and economic model, oh, this is actually reversed. Oh no, sorry, this is correct. Okay. Outperform those of black box models on out-of-domain tests, despite the fact that the black box methods actually have lower out-of-sample prediction errors within a given domain. So these results provide support for the intuition that economic models learn regularities that are general across a variety of domains, while these more flexible black box methods are sometimes learning regularities that are idiosyncratic to a given domain, in a sense thus overfitting to the domain. Okay, great. Thank you for the questions, and happy to take more. So I see one again in the back.
Several questions.
Thank you for the nice talk. Just when you thought there was a comment a minute ago, some people in the audience were laughing when you asked for useful applications of Rademacher complexity.
Right. Hopefully, because are they laughing because there aren't any, or because
perhaps? So I guess I'll ask my question because you said it's your first time giving the talk and you welcome feedback.
Mm-hmm. Yeah.
I'm not a machine learning person, but I'm just kind of thinking of this from like the point of view of someone who does maybe deep learning or neural nets. Like my understanding is that they're so super flexible that they can do anything. So if they're not doing as well as your other model here, your economic model, then I think somebody would just say that and you didn't tell us much about your neural network architecture and all of this. So I think they would just say, well, you didn't, optimize your hyperparameters correctly. Right? Like you just didn't explore the space of possible neural networks sufficiently. And that's why your economic model is outperforming. And moreover, your economic model seems to have some domain information, such as losses loom larger than gains, which I guess you could feed to your neural network as well. So it seems to me that with the right neural network design, you should get exactly the same thing as what your economic model is telling us.
Okay, that's a very interesting and somewhat provocative comment. So okay, let me say 2 things in response to that. So the first is we're not trying to conclude black boxes are worse than economic models. Okay, we certainly don't have that. That's way more sweeping, right? We have that in a specific application. It looks like CPT, a specific economic model, does better than 2 specific black box algorithms at this transfer prediction task, right? So we see the contribution of this paper, not as saying that, not as providing a definitive ranking of these different methods, but rather as providing a method that you can apply for any algorithm you have in mind, right? So suppose you go ahead and you do tweak the neural net that we've been using, right, and you improve it. Great, now we can come back and apply these results again, produce the same confidence intervals, look at whether it is in fact true that that tweaked version of the neural net actually improves upon CPT and the random forest. Right? So we want to provide this method that can be used in any of these cases to compare these methods by the transfer performance. And I actually think it would be super interesting if somebody did actually start looking at ways of merging insights that we've built into CPT. If we took those insights and built them into these different deep learning techniques and try to actually to see whether there's actually a method that's going to achieve not just this better out of sample performance within domain, but even better transfer prediction performance. That would be very cool, I think. But it actually is possible, really, that there is something about these low-dimensional economic models that do just provide better generalizability. I agree it's an empirical question. We would have to find out. Was there a question also in the back?
Yeah, sorry.
Yeah.
So I think one question I would have.
Sorry,
here,
could I jump in first? I had my hand up. It's of course right that machine learning algorithms do better if you tune their features, but I just want to understand this point conceptually and make an equally provocative response. I mean, in principle, couldn't we just add the certainty equivalence predicted by CPT as features into a neural net and let it use that, and then it would trivially always do at least as well? Is that, I mean?
Yeah, no, that's a great point, right? So that further goes to this, right? The distinction between economic models and these black boxes is not that clear, right? So as the question was indicating, it's not really that we're trying to say, right, all neural nets are going to be worse. Certainly, these black box algorithms that are taking as input the economic model's predictions is likely going to be doing better, and that's a very interesting direction for future work.
Okay, so very briefly, I will just say in biophysics, we often use like neural nets or linear models to predict the parameters on an individual level that we then feed into biophysical models. You could obviously do that here, right? So you could individually predict using a linear model or a neural net the parameters that you feed into CPT instead of like fitting those on whole populations. You'd fit them on individuals and you'd use this kind of some linear or neural net parameterization there. But that's just, a comment in conversation with what has been talked about.
Yeah, and it's almost like an inverse of what Drew was saying.
Yes,
so instead of feeding the econ model into the black
Yeah.
box, you want to somehow fit the black box into the, okay. Interesting.
Yeah. And that's very common in biophysics now. But anyway, more generally, I'd be interested in whether these generalization issues / gains are driven by shifts in the relationship between X and Y or shifts in X, right? So in computer science, we've kind of done a lot of work on kind of John Ducci's stuff and his group stuff on distributionally robust optimization, and more recently kind of Omer Reingold and his kind of community stuff on kind of multi-calibration. And those things are designed for when there isn't kind of confounding, right? So like the relationship between X and Y is not changing. The change in the distribution in Y is driven by changes in the distribution of X between domains, right? And so I would be interested to see how kind of neural nets or random forests trained with DRO would work here. Like, is the issue that there is unobserved confounding that is drawn kind of in this IID way from some like global distribution between samples, or is it driven by differences between populations in the different samples, like differences in X that are inducing distributions in Y?
Yeah, fantastic. So first, I can't, because the screen's very small, so I can't actually see who's asking the question, but I would love to follow up and get those references that you're mentioning. But I think what you're saying is exactly in line with what we're finding here, right? So the 30 samples in this paper exactly had the feature that the X space was the same, right? So there was a little bit of variation in the conditional distribution of Y given X, but because all the domains have the same x's, it's not, this transfer prediction problem is in a sense less demanding, right? On the other hand, when we're transferring across papers, now actually the X space is different across, so for us that means the set of lotteries, okay, but that's going to be different across the different samples. And that's exactly when the black box method does worse. So this upper tail is consisting of transferring across these very different sets of lotteries. So our understanding is that that's really what's tripping up the black boxes compared to the economic models.
Okay. Yeah. Thank you.
Another question?
Yeah, I had just one question regarding when you did the transfer Rademacher complexity. Did it give you anything in terms of like scalings and parameters that were informative? Like, did it have a, I don't know, a form that was helpful? I would kind of argue that the value of Rademacher complexity isn't to be a good bound per se, but is to give us some nice like worst case scaling or worst case intuition of like, this is how a number of parameters should scale. Like classically in linear models, right? We would say, well, okay, I need my a number of measurements to go like d over epsilon squared to get an epsilon bound. And of course, the constant in front of Rademacher would be hopelessly pessimistic for it to be useful, but still like d over epsilon squared would be a useful number.
Got it. So we didn't really see any insights like that. We could yeah, go back to that and check or to think harder about that. But I think part of what your question is getting at is there's like a difference between qualitative insights that we get from these asymptotic results versus like the practical usage of these intervals for these bounds for finite samples. And I think especially when we're thinking about something like transfer prediction, then having finite sample bounds really becomes extra important, and also bounds that are valid for small n, because we felt actually extremely grateful that we were able to construct a metadata set with 44 domains. In general, it's just having a large number of domains is not going to be feasible for many problems we're interested in.
Another question here?
Hi, thank you so much for your talk. I was wondering, I had a question on the analysis at the end when you're choosing kind of different choices for the domains. I was wondering whether the choice of which domains you have affects how well the IAD assumption is satisfied, and whether that would affect the analysis and conclusions at all as well.
Yeah, no, that's a great question. I think of it almost as the choice of domains is your IAD assumption. So whatever you think is IAD, that should be your definition of domains. Right. So maybe you think that data sets across papers are drawn independently, or maybe you think that data sets over sample pools. I think that in practice, it's not that easy to think through what the correct independence assumption is. But you're exactly right that there's this equivalence between how we're defining domains and what the IAD assumption means in our framework.
More questions?
Sorry, one last question.
Yeah,
So pretty common since 2019 in conformal stuff is to do conformal quantile regression. I'm wondering if you guys have thought about that and how that might give you, obviously you can't get conditional validity with conformal, but you can get more individual level confidence intervals if you do that kind of thing. I'm wondering if you don't think that would work because the samples are too small.
I think actually maybe you're referring to this. So we do provide confidence intervals for the quantiles of these distributions. And those intervals will in fact shrink as the number of domains gets larger. So I just had to skip it in interest of time, but the results we get here are really quite similar. So we still get these wider and higher upper bound confidence intervals for the different quantiles of this distribution.
Great. Well, thanks for all the questions, and let's thank Annie again.
Thank you.
So we have a 20-minute break now, and we'll be back at 11 o'clock for the next talk of the session.